Problem 9.53 says, in an article by Nancy Helmich, it was claimed that the typical supermarket trip takes a mean of 22 minutes. Now, in that first sentence, we're told something about means. So we're talking about how long a supermarket trip takes, and notice that we've already been told that it's been claimed that the mean is 22 minutes. Now, at that point, I know that this question involves means, and by talking about a typical supermarket trip and talking about it in that general way, the mean of 22 minutes is referring to a population mean. So that claim is in relation to the population mean of supermarket trip time. Now, if we keep going with the wording, suppose that in an effort to test this claim, you select a sample of 50 shoppers at a local supermarket. Okay, so we've got a claim about a population. We're going to test the claim. As soon as I see that word test, I'm thinking hypothesis test. And of course, in a hypothesis test, we use a sample as our evidence. We're sampling 50 shoppers, so that's going to be my sample size. If we keep going with the question information, we're told the mean shopping time for the sample of 50 shoppers was 25.36 minutes with a standard deviation of 7.24 minutes. Okay, so in terms of my sample of size 50, I have a sample mean, so an X bar value of 25.36, and I've got the sample standard deviation, 7.24 minutes. Using the 0.1 level of significance, is there evidence that the mean shopping time at the local supermarket is different from the claimed value of 22 minutes? So if I was in any doubt that this question was asking me to do a hypothesis test, seeing that level of significance confirms that it's definitely a hypothesis test that I need to conduct. And, we're talking about, is there any evidence? So we've got all the elements there to tell us that this is a hypothesis test. We want to see if the mean shopping time at our local supermarket, where we did the sample, is different from the claimed value of 22 minutes. So in using that keyword different, the thing I'm thinking about at this stage in the problem is that I'm going to be doing a two-tail test. Equals, not equals. Remember, when we just talk about testing to see if a result is different and we don't specify direction, there's nothing in the wording of this question that says we want to see if the shopping time is less than 22 minutes or more than 22 minutes, just that it's different from 22 minutes. So that tells me I'm going to be doing an equals versus not equals hypothesis test, which is a two-tail test. Direction is not important, so it's a two-tail test. Okay, so if we set it out using our standard format, I like to just sort of write some information as I'm reading. You can highlight or underline. So I've just got a little initial note saying, well, my claim is about the population mean mu, and it's that it's 22. I don't know population standard deviation. Of course, I'm on the lookout for that, because when we're talking about means and we're doing statistical inference, we've said all with the different topics, we need to distinguish between the situation where sigma, population standard deviation, is known and where it's not known. Here, we've only got the sample standard deviation. There is nothing about the population standard deviation. So sigma is unknown, and that means I'm going to be using the t-distribution. So I don't think it hurts to make a few notes as you start to read through the question, or whether you want to underline or highlight. Once I've sort of decided, okay, it's a test for means, it's sigma unknown, so it's a t-distribution test, and it's going to be two tails because direction is not important in this particular case, well, then I can start setting out the proper notation and layout for a hypothesis test. So we must write down the null and the alternative. So H0 is mu equal to 22. Remember, the null hypothesis always involves equals. Then the alternative is that mu is not equal to 22. and that's because we're only looking to see if it's different from the claimed value 22. So it's either equal to 22 or not equal to 22, and our alpha is 10%, 0.1. Okay, so I've then just listed my other information from the question. As I said, you can highlight or underline. I like to just rewrite it to make sure it's nice and clear and I don't lose track of what I'm doing. I've got my sample mean x bar, that's 25.36. That's going to be my sample evidence. I've got sample standard deviation S, which is 7.24, and I know my sample size n is 50. I like to start by then drawing up the decision diagram. Because this test is based on the t distribution, I draw up a t decision diagram. When it's the t distribution, I need to know the degrees of freedom, and for a test of the mean, when it's just the one population, degrees of freedom is n minus 1, so sample size minus 1, and in this case that gives us degrees of freedom of 49. Now we know it's a two-tailed test, so there are going to be two rejection regions, one in the lower tail, one in the upper tail. Alpha is 10%, so that's the total reject region size. Because this is a two-tailed test, we must split that 10% over the two tails. So I have a 5% lower reject region and a 5% upper reject region. I draw that onto my diagram, and then I just need to find the critical values, so the cutoff points. Now I go to my inverse t table. I go to the 49th row because it's 49 degrees of freedom, and I can look up the upper tail cutoff value because that's how the t tables work. So if you read across the 49th row, so 49 degrees of freedom, and you go across to the value that's in the 5% column, 0.05 column, the cutoff is 1.6766. Now you can round that off if you want. That's the positive upper tail cutoff, and of course t is symmetric, so the lower tail cutoff is then just the negative. That's one of the nice things about t. We can look up 1 and the other side is just the negative. So I have my decision diagram. Now I need to use my sample to calculate a test statistic to basically see where the sample falls. Is it in a reject region or is it in the non-reject region? The test statistic, it's always our sort of point estimate minus population result divided by standard error. So in this case, the point estimate, x bar, our sample mean, minus mu, population mean, divide by, and for this sampling distribution, standard error is s over the square root of n. So my sample mean is 25.36, that's my x bar. The hypothesized value for mu, the population mean, is 22. Remember, when you do a hypothesis test, you always proceed on the basis that the null is true. So if the null is true, mu would be equal to 22. Then you divide by s over the square root of n. Sample standard deviation s is 7.24 and our value for n is 50. Put that into your calculator and you come up with a test statistic of 3.28. So we can then look at that test statistic and compare it to the decision diagram. And we can see quite clearly that 3.28 would fall in the upper reject region. The cutoff is 1.67, so 3.28 is definitely in that upper tail reject region. So our initial decision is to reject null at an alpha of 10%. And of course, we don't just write our decision in terms of the null hypothesis, we then write it in relation to the alternative. So this is our chance to basically interpret the result and link it back to the problem. So we can say, because we've rejected the null, that's equivalent to saying there is enough evidence to conclude that the mean shopping time at the local supermarket is not equal to 22 minutes. So our sample evidence does not support the original claim, it actually supports the alternative.